So the first one says state the domain of the function. And so if I want to state the domain, I notice that I have part of my function in the denominator, and so I know that it will be undefined when the denominator equals 0. So we know that x cannot be equal to 0, but any other x value would give us something defined. So our domain is -infinity to 0, union 0 to infinity. Find the x-intercepts of the function, and so what I want to do is I want to set e to the x over x equal to 0. And so I can see that this is equal to 0 when e to the x is equal to 0, but I know that e to the x is never 0 because the function looks like that and it never crosses the line y equals 0. So there are no x-intercepts. Then use the first derivative to find the intervals on which the function is increasing and decreasing. So if I take the derivative, f prime of x, I can notice that the function is a rational function, so I can use the quotient rule. So I'll do, trying to put my skeleton there of the quotient rule. So it's going to be the bottom function times the derivative of the top minus the top function times the derivative of the bottom, and then square the bottom function. And if I set that equal to 0, that's, let's see, I'm going to simplify that. That's e to the x times x minus 1 over x squared. And if I set this equal to 0, I can set the top equal to 0. And that gives me x is equal to 1 here, and then e to the x is never 0 for any x, so that's all I get. And if I set x squared equal to 0, I get the place where the derivative is undefined, and it's undefined at x equals 0. So if I'm going to draw out my number line for f prime, I'm going to put 0 and 1. Okay, so those are, so 0 is where the function's undefined, 1 is a critical point, and so I want to see what is going to happen in between those values. So if I use the first derivative test, I can just plug in numbers less than 0. If I plug in something less than 0, e to whatever is always going to be positive. If it's negative, then I'm going to get something negative when I plug it into the x minus 1. And then if I do that, it's going to square it, so it's going to be a negative over a positive, which is negative. If you want, you can plug in an actual value less than 0 and see that you'll get something negative. If I plug in something between 0 and 1, the bottom part's always positive, e to the x is always positive, but if it's between 0 and 1, x minus 1 will be negative. So we'll get something negative over positive, which is negative. If I plug in something greater than 1, then this part, this x minus 1 part, will be positive, and everything will be positive. So it's positive. And so I can see that my function f is going to be, oops, not increasing, it'll be decreasing first. So my function f will be decreasing, and then decreasing, and then increasing. So it looks like x equal 1 is a local minimum. Then use the second derivative to find the intervals on which the function is concave up or concave down. So if I take the second derivative, maybe I'll leave it this way. So my first derivative, f prime, was x e to the x minus e to the x over x squared. So f double prime of x is going to be equal to low d high. So the derivative of x e to the x minus e to the x is going to be e to the x plus x e to the x minus e to the x minus the top function, derivative of the bottom, over the bottom squared. X squared squared is x to the 4th. So let's see if that simplifies. And so I can see here that that e to the x and that e to the x are going to go away. I'll have x squared times x, which is x cubed e to the x, minus 2x squared e to the x plus 2x e to the x. And so over x to the fourth, and so I can multiply I could divide the e to the x out and the x, and I'll have x squared minus 2x plus 2 and let's see, I can factor that, and that's going to give me, ooh, does that, so from that, I am going to see that, let's see, this part here is going to have complex roots, so I don't get any possible inflection points from that. X equals 0, we know is already an asymptote. E to the x is never 0, so I don't get any inflection points. No inflection points. But I still can look at my second derivative and see what's happening on either side of 0 to see if it's concave up or concave down. So if I plug in something less than 0, I'll get, let's just plug in -1, say e to the -1 is positive, -1, okay. E to the -1, and then I'll have times -1 times -1 squared plus 2 plus 2. So I'm getting something negative there. And if I plug in something greater than 0, let's just say 1 for example, I'll have e to the 1 times 1, and then I'll have 1 squared minus 2 plus 1, that's positive, over 1 to the 4th is positive, everything's positive, so I get plus. Okay, so it's concave down here, so f is concave down here and concave up here. And if I draw a graph of this thing, we'll just draw the graph. It's going to look like this. So it has a minimum there at x equal 1.